It can strike without warning at any moment. You may be walking across soft carpet and reaching for the doorknob when suddenly, zap!
To understand static electricity, we first need to know about the nature of matter. So, what is matter? Matter is anything that occupies space. All matters are made up of atoms that consist the three types of smaller particles: negatively charged electrons, positively charged protons, and neutral neutrons. Normally, electrons and protons in an atom balance out, which is why most matter you come across is electrically neutral. But electrons are tiny and almost insignificant in mass, and rubbing or friction can give loosely bound electrons enough energy to leave their atoms and attach to others, migrating between different surfaces.
When this happens, the first object is left with more protons than electrons and becomes positively charged, while the one with more electrons accumulates a negative charge. This situation is called charge imbalance or net charge separation. But nature tends towards balance, so when one of these newly charged bodies comes into contact with another material, the mobile electrons will take the first chance they get to go where they're most needed, either jumping off the negatively charged object or jumping onto the positively charged one, in an attempt to restore the neutral charge equilibrium. And this quick movement of electrons, called static discharge, is what we recognize as that sudden spark. This process doesn't happen with just any objects. Otherwise, you'd be getting zapped all the time.
Conductors like metals and salt water tend to have loosely bound other electrons which can easily flow between molecules. On the other hand, insulators like plastics, rubbers, and glass have tightly bound electrons that won't readily jump to other atoms. In the great outdoors, static electricity can be terrifying, destructive force of nature. In certain conditions, charge separation will occur in clouds. We don't know exactly how this happens. It may have to do with the circulation of water droplets and ice particles within them. Regardless, the charge imbalance is neutralized by being released towards another body, such as building, the earth, or another cloud in a giant spark that we know as lightning. And just as your fingers can be zapped over and over in the same spot, you better believe that lightning can strike the same place more than once.
Capacitor.
Capacitor. What is a capacitor? A capacitor is a component which has the ability or the capacity to store energy in the form of an electrical charge, producing a potential difference across its plates, much like a small rechargeable battery. In its basic form, a capacitor consists of two or more parallel conductive metal plates which are not connected or touching each other, but are electrically separated either by air or by some form of good insulating material such as waxed paper, mica, ceramic, plastic, or some form of liquid gel as used in electrolytic capacitors. The insulating layer between the capacitors is commonly called as dielectric. The conductive metal plates of a capacitor can either be square, circular, rectangular, or they can be cylindrical or spherical in shape, with a general shape, size, and construction of a parallel plate capacitor, depending on its application and voltage rating.
Parallel plate capacitor.
Parallel plate capacitor is the simplest form of capacitor. It can be constructed using two metals or metallized foil plates of of a distance parallel to each other, with its capacitance value in farads being fixed by the surface area of the conductive plates and the distance of separation between them. Altering any two of these values alters the value of its capacitance, and this forms the basis of operation of the variable capacitors.
To understand the nature of the capacitance of the capacitor, here is an example. By observing the current over time as capacitor charges to 6.3 voltage, we find a charge of 3.2 C on the plates. To compute the capacitance of the capacitor, we can use this equation C equals Q over B, whereas the value of Q is 3.2 and the value of B is 6.3. 3.2 divided by 6.3 is 0.51 and the unit is F. And here is and final answer. This equation can also be arranged to give more familiar formula for the quantity of charge on the plate as Q equals CV, whereas the value of C is 100 microfarads and the value of V is 5.5. 100 microfarads times 5.5 voltage is equal to 550 microcoulomb. You must wondering where did I get 5.5 times 10 to the power of negative 4 coulomb. So 1 microcoulomb is equivalent to 1 times 10 to the power of negative 6 coulomb. So 550 is equivalent to 500 times 10 to the power of negative 6 coulomb. To make this statement scientifically accurate, the answer must be 5.5 times 10 to the negative 4 coulomb. The magnitude of the charge of each plate is 5.5 times 10 to the power of negative 4 coulomb.
The capacitance of a capacitor.
Capacitance is also defined as being that a capacitor has the capacitance of 1 farad when a charge of 1 coulomb is stored on the plates by a voltage of 1 volt. Note that capacitance C is always positive in value and has no negative units. However, the farad is very large unit of measurement to use on its own, so sub-multiples of the farad are generally used, such as microfarads, nanofarads, and picofarads, for example. Since farad has a large unit of measurement, it uses sub-multiples for the examples. So first is the microfarad. So 1 microfarad is equivalent to 1 millionth or 10 to the negative 6 of a farad. So in order to get the value of 1 microfarad into farad, we need to move decimal places from right to left. So since it has negative 6 exponent, we need to move 6 places from right to left. So 1, 2, 3, 4, 5, 6. So the decimal is here. So the value of 1 microfarad is equal to 0.000001 farad. So that is how we will get the value of 1 microfarad into farad. So let's now move on to nanofarad. So 1 nanofarad is equivalent to 1 trillionth or 10 to the negative 9 of a farad. So 1 nanofarad is equivalent to 0.00000001 farad. Since it has negative 9 exponent, we will also move 9 decimal places from right to left. So that is how we will get the equivalent of 1 nanofarad into farad. Lastly is the picofarad. So 1 picofarad is equivalent to 1 billionth or 10 to the negative 12 of a farad. So 1 picofarad is equivalent to 0.000000000001 farad. Since it has negative 12 exponent, we will also move 12 decimal places from right to left so that we can get the value of
1 picofarad into farad. So that is how we will get the value of the submultiples of a farad.
Capacitance of parallel plate capacitor.
The capacitance of parallel plate capacitor. The capacitance of parallel plate capacitor is consists of parallel conductive plates X and Y. Each of area is separated by distance D. The positively charged Q is given to the plate X and the negatively charged Q is given to the plate Y. The median between the plates, or also known as the permittive of free space, has a constant value of 8.84 times 10 to the negative 12 farad per meter. Or in other words, the capacitance of a parallel plate capacitor is proportional to the area in meters squared of the smallest of the two plates and inversely proportional to the distance or separation given in meters between these two conductive plates. In the given illustration, the generalized equation of the capacitance of the parallel plate capacitor is epsilon times the quantity of the area over D.
To understand the nature of the capacitance of the parallel plate capacitor, here's an example. In a given parallel plate capacitor is composed of two plates that are separated by 0.5 millimeters. The dimension of each plate are 30 centimeters and 50 centimeters. Find the capacitance of the device. First, we need to determine the value we need to determine the given. For the distance, the value of the distance is 0.5 millimeters. And for the area, 30 centimeters and 50 centimeters. And for the permittivity of free space or epsilon, its value is 8.85 times 10 to the power of negative 12 farad per meter. Before we proceed in finding the capacitance, we first need to convert the value of the distance and the area into meters. So 0.5 millimeters needs to be converted into meters. And then every 1 meter, there is 1,000 millimeters. So 0.5 millimeters divided by 1,000. So the answer is 0.0005 meters, or it can be said as 0.5 times 10 to the power of negative 3 meters. And for the area, we also need to convert it into meters. And in every 1 meter, there is 100 centimeter. So 30 centimeter needs to be divided by 100. So 30 divided by 100 is equals to 0.3 meters. Same with the 50 centimeter. Divided by 100 centimeter, which is 0.5 meters. Now, we need to find the value of the capacitance. The formula in finding the capacitance is C equals permittivity of free space or epsilon multiplied by the area divided by the distance. Then, we need to substitute the unit with the given. So C is equals to 8.85 times 10 to the power of negative 12 farad per meter multiplied by 0.5 meters and 0.3 meters over 0.5 times 10 to the power of negative 3 meters. First, we need to multiply the two values of the area, which is 0.5 and 0.3, which is equals to 0.15 meters squared. After that, we need to multiply the value of permittivity of this space with the value of the area. So 8.85 times 10 to the power of negative 12 farad multiplied by the 0.15. So the answer is 1.3275 times 10 to the power of negative 12 farad. We then need to divide it with the value of the distance, which is 0.5 times 10 to the power of negative 3. And the final answer, or the value of the capacitance, is 2.655 times 10 to the power of negative 9 farads, or 2.655 nanofarads. If ever the problem is looking for the area, here's an example. In a given parallel plate, capacitor is composed of two plates that are separated by 0.5 millimeters and with a capacitance of 2.655 times 10 to the power negative 9 farad. Find the area of the plate. So we first need to determine the value of the distance and the capacitance. The value of the distance is 0.5 millimeters or 0.5 times 10 to the power of negative 3 meters. And the value of the capacitance is 2.655 times 10 to the power of negative 9 farad. And the value of the permittivity of free space is 8.85 times 10 to the power of negative 12 farad per meter. In finding the area, the formula we're going to use is A is equals to capacitance multiplied by the distance and divided by the permittivity of free space. So, after determining the formula, we can now proceed in substituting the values of the unit. So A is equals to 2.655 times 10 to the power negative 9 farad multiplied by 0.5 times 10 to the power negative 3 meters over 8.85 times 10 to the power negative 12 farad per meter. 2.655 times 10 to the power negative 9 multiplied by 0.5 is equals to 1.3275 times 10 to the power negative 12. We then need to divide that with the value of the epsilon, which is 8.85 times 10 to the power negative 12. Finally, the answer or the value of the area is 0.15 meters.
Capacitor and series. Capacitor are connected together in series when they are daisy chained together in a single line with capacitors in series. The charging current flowing through in the capacitors is the same for all capacitors as they only one path to follow. This example, this is what we call capacitors hooked up in series. Now, let's proceed to our example. Our example is we will gonna solve these three capacitors. This capacitor here, which is capacitor 1, capacitor 2, capacitor 3, and using this formula. Now, what I said, this is the capacitor series. This is the example. Is capacitor 1 stands for 4 farads, and the capacitor 2 stands for 12 farads, and the capacitor 3 stands for 6 farads. Now, we're gonna solve this and find the charges of all capacitors on my sample. Now, we're gonna use this formula, which is 1 over capacitor equivalent equals to 1 over capacitor 1 plus 1 over capacitor 2 plus 1 over capacitor 3. I'm going to use this formula, and this is capacitor 1 over capacitance equivalent, and 1 over the capacitor 1 stands for 4 farads plus capacitor 1 over capacitor 2 stands for 12 farads plus 1 over 6 farads, which is if you sum them all, you can get 1 over equivalent equals 0.5, and you will gonna divide the 0.5 into 1 to get the 2 farads. 5. So that we get the total farads of the 3 capacitor, which is 2 farads. Now we will solve and find the charges of 3 capacitors, which are we gonna use this formula, which is capacitance equal to charge electric charge over voltage. Now, to get the all charges of 3 capacitors is easily convert the total of 3 capacitors, which is 2 farads. Now, to get the charges of 3 capacitors is we will use the formula capacitance equal to electric charge over voltage. Now that we get the total of the farads of the 3 capacitors, which is 2 farads, we will easily put or change the capacitor here to 2. Now that we get the total unit of farads of the 3 capacitors, which is 2 farads, and now we will find the charges of these 3 capacitors, which is we are going to use the formula, which is capacitance equal to electric charge over voltage. Now, we will easily change the capacitance into 2 farads, which is this. We get the 1 capacitors over electric charge, and the 9 voltage here, we will easily put here the 9 voltage, and we will multiply them by 2 times voltage equals electric charge, and we will multiply them and get 18 capacitors of 1 electric charge.